Hi everyone, welcome to my channel Tech Tutorials 2K21, and today we are going to learn about a Prim's algorithm which is used to construct a minimal spanning tree in design analysis of algorithms. So this is an algorithm. So this algorithm is used for constructing a minimal spanning tree, and then here the input is taken as a weighted connected graph. So now the graph will consisting the vertices and edges, and then the expected output is, so we have all the edges are connected, which is used to form a tree, and the set of edges which is composing a minimal spanning tree of a graph G. So now initially what we have to do is we have to take, means these are the vertices we are including in a tree. So initially we are considering the initial vertex. So that is V naught. Means the set of tree vertices can be initialized with any of vertex. So you can consider any vertex. So you can start from any vertex from the spanning graph, and you are going to construct a spanning tree. So here initially we don't have any edges. So edge is initialized with null. And then here we have a for loop. So now these for loop, we are going to run from 1 to V minus 1. So all the vertices minus 1. So what we have to do? We have to find the minimum edge. Okay, we have to find the minimum edge. So we are doing these things repeatedly. Because of that, we are making here E star equals to V star U star. So what we can consider, suppose we have a vertex from V1 to V2 we consider, then you can take like V2, V1. So like this we have to take among all the vertices VU such that V in VT. So which are the vertex we can choose in, and that we are including into the vertices of tree. Okay, and union U square. So U star is nothing but already visited. So this indicates already visited. Okay, already visited vertex. And then ET is nothing but the edges we are including in a tree. Okay, so which consisting of minimum cost. So that is the meaning of this. So now at last you're going to return a tree which consisting of all the edges, which is used to construct your minimal spanning tree. So consider this example. So this is an example we consider. Okay. So here we have different vertices like from V1 to V7. So totally we have 7 vertices. Okay. And we have number of edges. So here you can see V1 to V2 is 1 edge, V1 to V4 is 1 edge, V1 to V3 is 1 edge, like that. So these all are the edges. So now you have to construct a table. Okay, this is a table we are constructed. So initially, what are the assumption we made? Like your VT means the tree which consisting the vertex. So initially we are making as V naught, means the initial vertex what we considered. So here in our graph, so we can start with V1. Okay, so now what we are VT consisting, this is V1. And from that, I cannot see any other vertices. So I cannot have any vertices. Okay, and then the weight is also 0 because I'm seeing from V1 to V1. Okay, so the weight is 0. And then from this vertex V1, I'm trying to visit all the remaining vertices. So you can see which format you can take. If you have an edge from U to V and we are considered as V to E. Okay, so like this you have to consider. So from V1, I'm going to reach V2. So now I'm trying to find any direct edges is there from V1 to all other remaining unvisited vertices. So from V1 to V2, I have a edge with weight 4. So now how are you going to write? So I can reach from V1 to V2 with a weight 4. And then I can reach from V1 to V3. So we can write it as V3, V1 and with weight as 5. And now I can see from V1 to V4. Okay, I can visit from V1 to V4 with weight as 2. And now from V1 to V5, I don't have any edge directly. So now from V1, I cannot reach from V1. Okay, and the Distance is infinity because I don't know how far it is. And then the next vertex is V6. And V6 also from V1 to V6, I don't have any direct path. So now it is also considered as infinity. And V1 to V7 is also infinity. So I hope you understand how we are getting this first step. So after this, what we have to do, we have to find the edge with the minimum cost. So among of all these edges, we can see that this will be the minimum cost. So now you can consider this vertex and you can include this vertex into your VT. So initially we have V1. So now you have a vertex V4. We have to include V4 into your vertices. So now from V4 and V1 we considered and 2. So whatever we have here, you have to write it here. And then from this V4, as of now, you have V1, V4 is visited and all the remaining is unvisited. What are the unvisited vertices? V2, V3, V5, V6 and V7. We repeat the same for all the remaining vertices also and we are trying to visit. Right? And here at this point, you can consider, okay, and you have to keep one thing in your brain. Suppose if you are trying to find an edge from one vertex to another vertex, you can see that there is no direct edge. So then what we have to do? So we have to find out whether we have any other edge which we can find from already visited vertex we have to consider here. Okay, that is the first step we have to remember. And second step, even we have a direct edge with a maximum cost, and this will gives you, right, the maximum cost, and we are finding another alternative path which is from already visited vertex, that is an indirect path. So among of this you have to consider the minimum cost. Okay, so let's see here. So here from V4 I'm trying to visit V2. Yes, I have a direct path, so I'm including from V2. From V4 I can see V2 and the weight is 1. So now you consider this one. And after that, from V2 to V3, so I don't have any direct path. Okay, now I consider V4 to V3, I have a path 8. Okay, I have a path 8. And as of now, V1 is already visited and I can see from V4 to V3 with V1. So now what I'm trying to do, so I can see this path 5 plus 2 is 7 and this is 8. Which one is minimum? This indirect path is minimum. So instead of I'm visiting from V4, I'm trying to visit from V1 to V3 with a minimum cost as 5. That is 5 plus 2 is 7. Okay. And after that, from V4 to V5. So from V4 to V5, I have a path with a cost 3. So I can include that. And from V4 to V6 also, I have a path with a minimum cost 4. I have to include. And V4 to V7 also, I have a direct path and I can include. So now we can find out that among of all, this is having the minimum edge. This is having the minimum cost on edge. Next, for this, you have to include this thing. So that is V2, V4, comma 1. So now what will be the visited vertex here? V2. So you have to include for VT. Okay, now you have to include V2. So from V2, what will be the unvisited vertices now? Now V3 is still unvisited, V6, V7 and V5. So now I'm trying to visit from V2 to V3. Okay, so I don't have any direct path. But I have different indirect paths. From V2 to V3, I can reach from V1, which is already visited, and from V4, which is already visited. And now you can see the cost is 4 plus 5 is 9, 1 plus 8 is 9. Both are same. So you can consider any one of that. And here I consider V1. So I can reach, right, I can reach V2 to V3 with the help of V1. So I can consider V1. What is the weight? Is 9. So now from V2 to V5, I have a direct path with a weight 2. So directly I am including this. So from V2 to V6, I don't have a direct path, but I have an indirect path with V4, which is already visited. So 1 plus 4, it is 5. 1 plus 4, it is 5. And then from V2 to V7, okay, from V2 to V7, I don't have any direct path, but I have a path with V4. So what is this path? 1 plus 7, that is 8. So you can consider this path 1 plus 7 as 8. Why? Because here I consider this, even I don't have any direct path, so which gives a weight as infinity. So now this will be the lowest cost as compared to infinity, so that I can consider this. So now you can see among of all these edges, now this edge is having the minimum weight. So you can consider this, that is V4, V2 and 2. So now you can add V5 to your list. So and after this, now all these vertices are visited and unvisited are still V3, V6, V7. Okay, V3, V6, V7. Now you can see I'm trying to reach from V5 to V3. But you can see that from V5 to V3, I don't have any direct path. But as of now, I visited the vertices like V1, V2 and V4. Okay, V1, V2 and V4. So now I'm going to find if any minimum path is there. Now I'm going to see from V5 to V3. Here it is one weight 11 and here it is another thing as 11 again. Okay, so this is one path. I can see like from V2, V1. So I cannot take two direct, indirect vertices. So I can go through a single indirect vertex, that is V4. Now I'm finding the weight as 11. So I can reach from V5 to V3 with the help of V4. So from V4, I'm trying to visit V3. Okay, and the weight is 11. So now from V5 to V6, again, I don't have any direct path. So I can see the indirect path from V4. So now I can visit 3 plus 4 is 7. So here you can see this is 3 plus 4 is 7. So now another unvisited vertex is V7. So from V5 to V7, I have a direct path. So now I consider this, right? V5 to V7, I have a direct path and you have an indirect path also, but the weight is 10 here. So now you consider this path only. So among of all this will be the minimum. So you have to consider this in a next step. So now you are considered here. Now you have to include here V6 also. So from that V1, V2, V4, V5, V6 is visited and still unvisited is V3 and V6. So now I'm trying to visit from this. So from V6 to V3, I have a direct path with weight 1. So I can consider this. And then from V6 to V7 also I have a direct path 6. So I can consider this. So now you can see among of these two, this will be the minimum cost. So you can consider this path for the next step. So now you are going to include V3 also in your visited. Okay. So now here I can see the unvisited vertex, that is V7. So now you can see from V3 to V7, I don't have any direct path. Okay. V3 to V7, I don't have any direct path. So, but I have an indirect path through V6, which is already visited. So I can consider 1 plus 6 equals to 7. And I'm going to reach from V6 to V7. So this is only the one thing it is possible. You can consider this for this. And you can include into your visited vertex. Okay. And then your V2 will consisting all your vertices. Okay, this is your final set of VT. And then what is your ET? So ET will consisting of all the edges. Right now you can consider the edges. So here we have an edge V1 to V4. Right, V1 to V4 is one edge we consider. And then we have the another is V4 to V2 or V2 to V4. Okay, you can take anything because this is an undirected graph, right? And then we have V2 to V5. This is also one edge we consider. And then we have V4 to V6. This is one edge we consider. And then V3 to V6. This is another edge we consider. And then we have V6, V7. Okay, so these are the edges we consider. Okay, these are the edges we consider like 1, 2, 3, 4, 5, and 6. Now you have to connect those edges. You can see like V1 and V4 is connected. Right, you can connect this. like V1 and V4 is connected. V1, V4 is connected. Okay. And then V4, V2 is connected. So you can connect this also. V4, V2 is connected. And then V2, V5 is connected. Means these two. Like you can consider this edge. V2 and V5 is connected. And then V4 and V6 is connected. Where is V4, V6? And here it is. You can consider this. V4 and V6 is connected. And then V3, V6 is connected. Now you can consider this edge also. Okay, V3 and V6 is connected. And then V6, V7 is connected. So now you can see this is your graph. You can see all the vertices are connected. V1 is connected, V4, V2, and V5 is connected. And here V6, V3, and V7 is connected. So after we connecting all, we can see this is. Okay, this is your output. So we can consider this is your output. And what will be the minimum cost here? So you can see the minimum cost is nothing but, right? You can add the cost of all the edges. Now 2, 1, 1, 4, 6 plus 2. So what is this cost? 4 plus 4 is 8 and 8 plus 2 is 10 and 10 plus 6 is 16. So the minimum cost of this spanning tree is 16. So this is a Prim's algorithm. I hope you all understand. Thank you. So if you have any queries, you just message me in chat box. Thank you.